Testing. Okay. Yeah. Should I get started? Sorry. Okay.
Okay, welcome everyone. And today we have at the end of this meeting, we will go out to have a group photo of the ITC members, and everyone is welcome to join us. It's a beautiful day. We planned it ahead of time. We had a discussion today about what we don't understand about the cold and hot phases of the interstellar medium. Jesse was leading it. And, thank you, Jesse, for a very nice conversation. Today we have 4 presentations, 2 of them from MIT nearby. The first is by Jacob Shen, and he will talk about the implication of the UV variability for the abundance of bright galaxies at the cosmic dawn. And of course, that's a hotly debated subject. A lot of people think maybe lambda CDM is off the table. Others say no, it's just galaxy properties. Today we'll hear one version of the story. We'll also hear from Rahul Jayaraman. Is Rahul here? Yes. And he will tell us about finding and characterizing gamma ray bursts with TESS. That will be very interesting. And then we'll hear from Claire Lamman here at Harvard. Where is Claire? Oh, over there in the corner. And she will tell us about the intrinsic alignment of DESI galaxies. And finally, from Igor Chilingarian, we heard him last week at the discussion from here at the CFA. And he will tell us about an active binary intermediate mass black hole. Go ahead, Jacob.
Thanks, Avi. I'm Jacob. I'm a new postdoc at MIT. My talk today will be about the UV variability as a potential solution for the large abundance of bright galaxies at cosmic dawn. And in the early science and cycle 1 observations of JWST, a large abundance of UV bright galaxies has been reviewed, and it exceeds the predictions essentially from the majority of the theoretical models. On the left, I'm showing an example from the SEER survey, and the gray band here shows the surface density of bright objects above a certain redshift, and is compared to these colored lines, which are theoretical model predictions from either empirical models, semi-analytical models, or hydro simulations. And this tension exists even when only considering the spectroscopy confirmed galaxy samples so far, as shown by this hurricane in 2023. And this implied lower limit of the UV luminosity density at redshift above 10 is still higher than the predictions of theoretical models built before the JWST era. And there are already many solutions and debate in the literature about this tension. Well, one solution I want to highlight today is the UV variability. And it describes the scatter of galaxy UV luminosity at fixed halo mass. And the reason scatter works is that the halo mass function is always steeply decreasing towards the massive end. This ensures that if there are some symmetrical scatter, there will always be more low mass halos upscatter to brighter luminosities than massive halos downscatter to faint luminosities. So the net effect is that the brighter end of the luminosity function will be populated. And this variability as a solution may require no major revision to the current standard galaxy formation model. It's just the variability is somewhat underestimated. And there are well-motivated physical drivers for potentially large variability. For example, the bursty star formation in low mass or high redshift galaxies found in zooming hydrodynamical simulations. And to really quantitatively tell what level of variability would be required to reconcile this tension, we need some reference model. So in the following, I describe a very simple empirical approach to translate the halo mass function to the observed galaxy luminosity function. And we'll start from the halo accretion rate and convert it to the baryon accretion rate of the halo, and it's all determined by cosmology. And then we connect it to the star formation rate, assuming the concept of a halo scale star formation efficiency. And it is assumed to depend on the halo mass, but independent of redshift. And this type of model has been widely used in previous empirical modeling work. So that's why we choose it as more like a benchmark here. And despite different function form and parameters assumed, they all point to roughly 1% of star formation efficiency at a halo mass scale of 10 to the 10, and it will gradually increase to about 10 to 20% in a Milky Way mass halo where it peaks. And then we connect it to the intrinsic UV photon production rate of galaxies. And this depends on the age, metallicity, and the initial mass function of the stellar population. But as shown by this Madon and Dickinson's work for typical star formation history and metallicity of high redshift galaxies, it tends to have a stabilized value. And then we model dust attenuation with an empirical approach that's often used in observational work. It combines the relation between the infrared excess and the UV continuum slope, and the relationship between the UV continuum slope and the UV magnitude. It forms an empirical mapping from the UV magnitude to the attenuation in UV. But our result is actually not too sensitive to the uncertainties in modeling dust attenuation. And this together forms a median mapping from halo to galaxy. On top of that, we add the variability. We model this by doing a convolution of the raw luminosity function with a kernel function. And this kernel to first order is assumed to have a log normal distribution of UV luminosity around the median value, characterized by a single parameter, which is a scatter, sigma UV. It's a scatter of UV luminosity in logarithm. And again, this cartoon shows why there will always be more upscatter compared to the downscatter, and this will preferentially populate the brighter end of the luminosity function. And here are two plots comparing this prediction of this very simple empirical model with JWST observations. And all these color lines are models assuming this canonical halo mass dependent star formation efficiency pairing with some level of variability. And all these background faint blue lines are even simpler models assuming a constant star formation efficiency across all halo mass and no variability. But the point I want to make here is that this canonical star formation model can be reconciled with JWST constraints by assuming some level of variability. If we look at the bright end at around redshift 9, it appears that a sigma UV of around 0.75 magnitude is preferred. And this is quite consistent with the choice of many previous empirical models built in the Hubble era. But if we move to higher redshift, it appears, for example, at redshift 12, a sigma UV of 1.5 to 2 magnitude is required. And here's a summary plot showing what kind of model variations is required to meet different levels of JWST constraints. One direction you can go is to systematically enhance the UV photon yield. This can be done by, for example, systematically increasing the star formation efficiency or assume a top-heavier initial mass function. And the conclusion on this direction is that you need a factor of 4 or 7 boost in UV photon yield to be consistent with the spec-Z or photo-Z constraints of JWST. While in a orthogonal direction you can go is to assume some enhanced UV variability, and this will greatly reduce the need of a boost in UV photon yield. And for example, with this fiducial benchmark star formation efficiency model and the salpeter initial mass function, a sigma UV of 1.5 magnitude can get you consistent with the spec-Z constraints of JWST. Well, if you assume a Chavarri or Kropa IMF, it reduced to 1.3 magnitude. And there are indeed many potential sources of UV variability. But the first is the halo accretion rate, the scattering the halo accretion rate. And it has been measured by in-body simulations. And the value often quoted in the literature is 0.3 DAX. It's actually the motivation for the choice of sigma UV by many previous empirical models. But on top of that, there could be additional variability contributed by all the baryonic processes happening in the galaxy. For example, the baryon cycle on the CGM scale, the clustering of star formation in both space and time in the interstellar medium, or in the smallest scale, the life cycle of individual giant molecular clouds. And further variability can be driven by the time and site life variations of the dust opacity as well. But to really tell how these different sources of variability aggregate, we need a theoretical framework that has predictive power in this regime and can actually resolve the relevant physical processes that drives UV variability. So that's why we look at the FIRE2 high redshift simulations. It is a suite of cosmological zooming simulations of galaxies at redshift about 5. They are originally presented in Xiangchun Ma's work in 2018 and 2019, and now are publicly available. What's remarkable about the FIRE is that it has great spatial and mass resolution. It pairs with this remarkable resolution with necessary physics models for star formation and feedback processes within a resolved multi-phase ISM. And from this movie, you can already identify several features that might drive variability. This multi-phase structure of the interstellar medium, this breathing mode on galactic scale, and this clustering of cold gas clumps or star form. And in this recent work led by Jason Shen, we indeed try to measure the scattering UV magnitude in simulated galaxies at the redshift and halo mass range of interest. And we indeed find the level of variability is quite consistent with what we infer from the simple empirical model. And if you look at the luminosity function, it is remarkable that the out-of-the-box prediction from FIRE matches the JWST constraints. And if you try to artificially smooth the star formation history of simulated galaxies, you would get a dramatically different shape at the bright end. So unable to resolve the relevant physical processes that drives large variability might be the reason that some theoretical models underpredicts the abundance of bright galaxies. So here are some takeaways of my talk, and I'm happy to take questions.
So Jacob, of course, there is another potential so-called magnification bias in the context of gravitational lensing. It's exactly the same effect that if you have lenses along the path, they would bring low luminosity galaxies to the high luminosity beam. And as you go to higher redshift, you would expect that to be more important. The optical depth of gravitational lensing is higher. Is that ruled out?
I don't think it's ruled out, but I think it depends on really how the observational community take care of that uncertainty. But by reading those papers, I'm pretty sure they at least have some consideration about the lens magnification. And it's just uncertain how accurate they measure that.
Well, of course, if there are two images, they could tell, but sometimes you get just magnification of one bright image, and the question is whether they know if that is at play or not. Because you would expect it to appear at high redshift. The optical depth is high.
Yeah, I completely agree with that.
It's worth checking, because it's the same effect as you are describing coming from completely different physics.
Yeah, exactly.
Yes, go ahead, Tony.
So I was going to mention the gravitational lensing, but another effect is whether or not these objects have AGN, right? And if they have AGN, they could be the AGN itself could be highly variable, and it may be buried under a lot of dust, but nevertheless increasing the overall luminosity of the object. And it's a kind of random thing that's just thrown in there, and obviously exists for a lot of these things, but not others.
Yeah, I think that's really possible, and it's actually a section that I trimmed out in my talk. So I think like there are some recent observations suggesting really large faint abundance of faint AGNs, and well, if it's really that abundant, then this could create a level of contamination for galaxy UV luminosity. But I think I would wait a little bit time for these measurements to really converge. But yes, AGNs are also like one potential solutions to explanations to this tension. Exactly.
To keep in mind about AGN is that there is the so-called Eddington time, which is the time it takes the black hole to double its mass as a result of accretion. And that is a constant. It depends just on fundamental constants. And as you go to redshifts above 10, the age of the universe gets close to that. So this time is typically for quasars a few times 10 to the 8 years. And once you go above redshift 10, that's roughly the age of the universe. So it means that AGN have a duty cycle of order unity. They operate most of the time.
Yeah. Well, I think it depends on whether you can have super-Eddington accretion and what mass seed you grow from. You compare a relatively low mass seed with super-Eddington accretion with potentially a low duty cycle to produce these objects, but you can also have a relatively massive seed with a sub-Eddington accretion.
Any other comments? If not, let's thank Jacob again.
Thank you.
All right. Can everyone hear me?
Yes.
Cool. Okay. This works, I think. All right, perfect. All right. Hi, everyone. My name is Rahul, and I am currently a fifth-year PhD student at MIT just down the road. And today I'll be talking about detecting and characterizing GRBs using the Transiting Exoplanet Survey Satellite, or TESS. So in this talk, I'll give a brief introduction to TESS and a description of some of the optical emission that we're hoping to observe from these GRBs. And then I'll talk about the blind search pipeline that we've been developing in TESS for transients. And then to close out, I'll talk about some of the things that we've already learned from GRBs that have been observed by TESS. So for those of you who don't know, TESS was launched in April 2018 with the express goal of detecting transiting exoplanets around M dwarfs. TESS has an over 2,000 square degree field of view and a 200-second imaging cadence for its entire field of view. And so TESS is made up of 4 cameras and 4 CCDs that allows it to have such a large field of view. The bandpass is monochromatic and comparable to the cousin's eye bandpass. So here is a plot of the TESS bandpass compared to the Pan-STARRS GRIZZY bandpasses, which are shown in dotted lines. So as you can see, TESS is very well suited to detecting transients that have a redder SED than some other space-based observatories. And the 3 sigma detection limit of TESS is around 20.5 for a 6-hour image stack. At the native cadence of around 200 seconds, the detection limit is around 17th to 18th magnitude. So just that sort of gives you a sort of sense of what types of things TESS is able to observe and discover. So TESS does a 2-year scan of the entire sky and stares at a particular region of sky for 30 days before shifting its field of view. And so over a 2-year scan, it's able to cover around 90% of the entire sky. The top plot shows the sky coverage of TESS throughout the first 5 years of its mission. As you can see, it's covered a very, very large part of both the northern and the southern sky. And this bottom picture is just a mosaic of all the TESS images from the first 5 years of the mission to just show like that TESS has really been able to observe a very, very large part of the sky. And so with TESS, we can discover exoplanets, but we can also identify GRBs and study their optical emission. And so we're looking for two key optical signatures of gamma ray bursts. The first is prompt emission, which is a bright optical flash that's usually contemporaneous with the gamma ray trigger. So these sorts of things are very, very difficult to detect from the ground because a ground-based survey or telescope has to be observing that region of sky at the right time in order to catch the GRB-associated optical flash. Or a robotic telescope has to be able to slew rapidly to the GRB localization region in order to observe this flash. But this flash is actually very useful because it can be combined with the high-energy SED from these burst monitoring satellites such as Fermi and Swift in order to constrain emission mechanisms within the jet. In 2019, Oganessian et al. Published a paper suggesting that the optical flash, when compared to the broadband SED at high energies, suggests that the initial emission from the jet may be related to synchrotron emission. The other optical signature that TESS is able to observe is the afterglow. And so the afterglow is fainter optical emission caused by the ejecta shocking the matter that's surrounding the burst. These are somewhat easier to detect, even though they are fainter, because they're much longer lived. In fact, TESS is able to observe these afterglows for hours, and in a couple of instances, it's observed them for periods of over a day. And so this is useful because properties of the light curve, including the decay slope, as well as the location of a power law break, can help us constrain the physical parameters of the burst from test data alone without detailed multi-wavelength follow-up or modeling necessarily. So as an illustration of what I mean by prompt versus afterglow emission, this is a plot of a recent GRB, 230307A. The left-hand side of the plot shows the TESS light curve. As you can see, there is a bright optical flash at the time of trigger. That's around 14.5 magnitude. And then there's a slow rise and fall that's associated with the afterglow. And so TESS was the only observatory that was actually able to detect this because the burst was initially poorly localized, but ground-based follow-up and Swift XRT follow-up was able to narrow the location to this particular set of coordinates. And so this lets me transition into a discussion of the two ways in which we've been approaching GRB detection in TESS. The first one is kind of the lower hanging fruit. So if there's already an arc-second level localization from Swift XRT for an afterglow, we can do forced difference imaging photometry at the location of this burst in order to see whether or not there was an optical signal in TESS. So from this analysis, which we've almost completed a paper on, we found 22 well-localized bursts that fell within the concurrent TESS field of view throughout the first 5 years of the mission. Of these, 8 had significant detections of either a prompt emission component or an afterglow. A more difficult problem is these poorly localized bursts. So a lot of the burst localizations from Fermi GBM and SwiftBat cover many square degrees, and so tiling these with ground-based telescopes or surveys is often infeasible. So TESS's large field of view allows us to sort of get this data for free. We're able to analyze any overlaps in the localization and the TESS field of view in order to identify any optical counterparts to these GRBs. However, we need to be able to be set up to conduct a blind search to find these unidentified optical counterparts in TESS. And if we broaden our search to the entire TESS field of view, we may also be able to detect orphan afterglows, or GRBs that lack a corresponding high-energy trigger. And so I'll briefly discuss the blind search pipeline that we've been working on to detect transients in TESS. So this pipeline is kind of a catch-all. It can catch everything from galactic transients all the way to extragalactic transients, such as GRB afterglows and supernovae. So we start out with difference imaging, as described in Michael Fosna's supernova papers from 2021 and 2023. We combine all of the difference images for a given CCD into an RMS image that tracks the variability of each pixel across the entire sector. We then run source extractor on this RMS image to identify strongly time-varying sources and cross-match with Gaia DR3 in order to eliminate known sources of variability, such as things like eclipsing binaries and flaring stars. We then classify each source with a probability of being a transient using a convolutional neural network that was trained on transients from the first 2 years of the TESS mission. And we're currently working on updating the training data and retraining this neural network for an increased detection sensitivity using the new 200-second TESS cadence. We then do photometry and create light curves for the quote-unquote best sources that we find. And then we do an additional layer of filtering using HDB scan to really zero in on those light curves that are interesting and could potentially represent actual bona fide transients. And we're also currently working on developing infrastructure for automatic public dissemination of these transient candidates via the TESS site for community-based follow-up. And so to close out, I'll give a brief summary of what we've already learned from GRBs that have been observed by TESS. And the paper is on the archive, and we're hoping to submit it sometime next week. So this GRB, 200412, was the most optically bright GRB that's been detected by TESS so far. It peaked at around 12th magnitude. And so TESS was able to observe this afterglow decay for more than a day. And it was able to observe two interesting features. The first is a late time flare at around 17,000 seconds post-trigger. That's around like 4 to 5 hours. It was also able to observe a steepening of the power law index in the decay light curve. And so with this, we're able to discuss whether or not this power law break arises from the geometrical jet break that's caused by the cooling ejecta as it becomes less collimated and the Lorentz factor decreases, or if it's the afterglow cooling break when the synchrotron cooling frequency passes through the TESS bandpass. And for this case, we think that this is likely the geometrical jet break, and that allows us to calculate the opening angle, all from just this light curve without anything else. We also observe an interesting flux excess at the start of this light curve. So because this data was taken when TESS was at a 30-minute cadence, this flux excess could also contain things apart from that prompt optical flash. For instance, it could contain signatures of the reverse external shock emission. And our analysis suggests that there may be some flux from the reverse external shock in that first point right there. But because TESS's cadence was at 30 minutes at the time, we're not able to get a more fine-grained resolution as to the nature of the light curve at that time. We also wanted to reiterate that early time light curves are super important. So this is some model light curves for GRB 210204A from Kumar et al. 2022. And the key takeaway is that they used a lot of late time data to constrain the properties of the GRB. But when you compare their model early time light curves to the TESS light curve, you find a significant discrepancy, and you find a peak that they predict that you don't see. And so this really emphasizes the utility of TESS in searching for GRBs. And so our next steps are to, once we're finished fine-tuning the blind search pipeline, to run it on these poorly localized GRBs, which there are around 80 to 100 of them throughout the first 5 years of the TESS mission. And then we also want to model the prompt spectra all the way from optical to high energies. We're also well positioned to rapidly respond to new GRBs that fall within the field of view. From the time the data is downlinked to the time that we put out a GCN, for the last GRB, it was less than 36 hours. And we're also working on an automated localization plotter for the overlap of the TESS field of view and the Fermi GBM or Swift-BAT localizations. That's based on the code that we wrote for the gravitational wave sky map overlap calculator. And I will leave this slide up, and I'm happy to take any questions. Thank you.
A shock breakout in a supernova or a gamma ray burst early on, TESS has the advantage that it's in space. So maybe from the time delay relative to ground-based detection, you could tell the localization.
Yeah.
That's all possible.
It is possible. The one thing is that TESS downlinks its data only once a week. And so if, for instance, so I think this week the data was downlinked on like Tuesday. So if a GRB went off on Wednesday, we wouldn't know about it until the following week. And so that, I think, is the one key disadvantage of TESS when compared to ground-based surveys. But if a ground-based survey were able to pinpoint the exact localization within that week, then we could go into TESS and create a light curve and then compare that to the ground-based data.
So yes, you've seen several afterglows. Is that-
Yes.
How many GRBs have you seen the prompt emission?
Yes, that's a great question. So we saw the prompt emission for 20.
You showed up one picture.
This one,
Yeah.
230307.
Yeah.
And we also saw prompt emission in, let me pull up the slide, in these two afterglows as well. Or these two GRBs, sorry. So 220623 had a 13 sigma detection at the time of trigger and no afterglow detection. And then 230903 had a 5.5 sigma detection at the time of trigger and a weak fit to a corresponding afterglow. So we've been able to see, I think, of the 8 that I mentioned earlier, 3 prompt detections. There may be a 4th one, but it was a 3.8 sigma significance, so we report that as tentative.
No, but that's a great success rate, I would say. Is it telling us anything about models?
Yeah, so that's the next step. So if we extend the models for the high energy SED, we'll be able to figure out which models are correct. Because past literature has found that the optical points can differ by many orders of magnitude from the extension of the high energy SED models. And so that's something that we haven't done as part of this work, but we're hoping to do within the next few months.
Great.
Yes, please.
Yeah, so let's say, for example, the GRB on the top,
Mhm.
can you detect this with your blind search pipeline?
Yes, so the blind search pipeline searches for these sorts of point sources. And so given that it's agnostic to the kind of point source, we should be able to detect it. But there are some other instrumental features that could also cause a point source like that. And so the temporal coincidence is very important in order to make sure we have a concrete detection of this sort of prompt emission.
What was the time lag since trigger for you
Uh,
for the detection? Because we can't read it. Was it a matter of seconds? Or?
Oh, so this was taken when TESS was operating at a 10-minute cadence. And so I think for this one, I don't remember off the top of my head, but I think the trigger happened, I think 300 seconds into the exposure or something like that.
Oh, wow.
Yeah.
That's quite impressive. Yes.
For this GRP for which you showed the replanting in the optical,
Mhm.
and you infer is due to the possible reverse shock. So I saw just 3 points from the Swift 6RT.
Yes.
Is there an achromatic rebrightening which will lead you to?
Yeah. So that's a great question. So one thing that we do mention is that there is not much data in other bands to really reinforce whether or not this is a geometrical jet break. So we think that it might be this jet break, but we don't know because we lack data in other bands.
Any other comments, questions? Oh, yeah, go ahead.
So, if you have these one-time events, how do you know that they're not just a cosmic ray hit on your CCD detector?
Yeah, so that's a good question. And so you're talking about the prompt, this one, right?
Yeah.
Yeah, that's a great question. So TESS has actually onboard cosmic ray mitigation in its flight software. And so in the paper, we give a more detailed description of how we sort of account for that and try and make sure that the things that we detect are not necessarily cosmic rays. And also, if the CRM algorithm does clip some of the emission that's from the GRB, like how we can add that back in to get a better estimate of the true optical brightness of the GRB. So basically, the short answer is it's kind of taken care of by the flight software. The long answer is there's a lot of modeling that goes into it.
But also the chance for a coincidence
Yeah.
would be very small because you know the rate of cosmic ray hits.
Exactly. The temporal coincidence is a really big sort of tell that we might be seeing a genuine signal.
Yes, Josh?
Yeah, have you investigated what your X-ray sensitivity is in these 4 CCDs that you've got? Have you done modeling of what the detection probability would be in the few keV band, which we know for most GRBs nothing about?
The sensors
Right.
is not sensitive. is it?
Yeah, TESS is optical to near infrared.
No, I know it's
okay.
an infrared and optical detector.
Yeah.
But that same CCD, depending on what your window of function is,
Mhm.
will have considerable area in the cameras. I would think it's easy enough to do the modeling. Have you
Yeah.
to see what the X-ray sensitivity would be?
That's a great question. We haven't actually thought
It'd
of
be
that.
better than you might suppose.
Yeah, we haven't actually thought of that, but I can ask.
Right now, there's only one instrument up there, there are probably a dozen now with CubeSats and whatnot, that has any information on the soft X-ray band, and that's MAXI.
Right.
But it's detected probably in its whole lifetime, just a few GRBs.
But Swift is still alive.
Yeah, it's still alive, but.
So Swift is still up there, yeah.
Sky, it would be interesting to really check that out.
Yeah. That's an interesting question. I don't know off the top of my head about the X-ray sensitivity, but I can ask George Wicker.
The whole classification scheme for GRBs is under debate now. The spectra is what is really important.
Exactly, yeah.
So the more that can be learned, the better.
Yep.
We have something that will do much better, but you're up there and flying, so go for it.
Well, let's thank Rahul again.
All right. Good afternoon, everyone. My name is Claire Lamman. I'm a graduate student here at the CFA working with Daniel Eisenstein. And today I'm going to be talking about a seemingly small effect that can have big implications for some of our measurements on the largest of scales. It's all about intrinsic alignments, or IA. Intrinsic alignments describe subtle correlations between galaxy shapes and the underlying large-scale density or tidal field. This is a direct result of our understanding of galaxy formation, and the general trends we see are that the long axis of red galaxies, or elliptical ones, are aligned with the stretching direction of the tidal field or some large filament, and then the spin vector of blue galaxies is pointed in that direction. This is a very small effect, so in order to actually see a signal, you need at least tens of thousands of galaxies. As a quick plug, I recently made a guide that goes over the common IA estimators and formalism, so if you're interested in learning a little bit more about that, you might want to check this out. Now, intrinsic alignments are quite inherently interesting for a lot of reasons I don't have time to go into right now, but most commonly, IA is known as a contaminant in cosmological surveys. This is because there's another way you can observe correlations between galaxy shapes and density: lensing. Now, IA is very small, so it doesn't actually matter for strong lensing like you see in this beautiful JWST image, but it is the main contaminant in weak lensing studies. However, today, I'm going to introduce another reason for why IA matters, one that I find particularly interesting because it actually mimics the signal that we see of redshift space distortions. So before I get too much into that, I just want to step back for a moment. For this problem, the most relevant question that we really care about is, how does the structure of the universe evolve? We can explore this question with a spectroscopic map of galaxies. On large scales, matter falls towards dense regions, and since we determine distances through recessional velocity, this creates a squashing in redshift space along the line of sight. But you don't see this distortion in the plane of the sky, so it creates a signal of anisotropic clustering. We quantify clustering with the correlation function. The monopole describes how clumpy the universe is, averaged over all angles, and the quadrupole describes how clumpy it is in one direction versus another. The real universe is, of course, isotropic. However, RSD creates a non-zero quadruple signature. This is quite useful because the quadruple signature is a direct result of the largest motions in the universe, the growth of structure itself. And interpreting this on small scales is difficult and complicated, but on large scales, it becomes linear. So RSD is uniquely suited to probing structure growth on large scales and the components which drive it, like gravity and dark energy. So different parameters of lambda CDM, I don't know if I have a laser here, will predict slightly different growth rates on the y-axis as a function of redshift. to distinguish between them, what we really need is a very precise measurement of the quadrupole, and for this, we need a really large spectroscopic map of galaxies. This is exactly what DESI is doing. The Dark Energy Spectroscopic Instrument is surveying over 40 million galaxies. You can see our footprint in the background here, which covers about a third of the sky. And right now, we're in the middle of our 5-year survey. We're gathering spectra using the 4-meter Mail telescope, which is on Kitt Peak, and it's special because the focal plane is comprised of 5,000 individually controlled robotic positioners. So basically, we can gather lots of spectra very quickly. Before DESI, collectively, people had measured about 3 million extragalactic redshifts over 20 years. And in the first year of DESI, we got 14 million. This builds upon the foundational work of the CFA Redshift Survey, which for the first time found evidence of a clustered universe in the form of the wonderfully flailing stick man. Now, I want to show this not only because of where we are, but because I thought it would be fun. I found the same slice in our year 1 data and made a comparison, so now we can be absolutely sure the stick man is not alone. Now, with great data comes great responsibility to think about every single source of systematic error. In particular, it turns out that galaxies are more than just points. For precision cosmology, we need to picture them as they really are, simple ellipsoids. So I'm sorry to everyone. So in particular, I mostly just think about luminous red galaxies, which are generally elliptical galaxies that are large, relatively dust-free, and are great tracers of the cosmic web. All right, halfway through the talk, I can now finally come back to intrinsic alignments and bring all of these ideas together. One reason we need to care about IA, particularly for DESI, is that it can create a fake RSD signal. The general idea is that if galaxy orientations are correlated with the underlying large-scale structure, as you see in intrinsic alignments, and there's a bias in those orientations due to, say, how a survey chooses its targets, you'll get a bias in how you measure the underlying structure. Specifically, you see an anisotropic signal. How this effect arises is not immediately obvious, so I've made a quick little animation to demonstrate it. Imagine you have the cute little Mail telescope looking out across 3 density filaments that are parallel to the line of sight. So you can think of this as a wave of density. I'll now put some elliptical galaxies on top of this that have maximum tidal alignment. So galaxies in the density troughs will be pointed towards the peaks, and ones in the peaks will be oriented along the top. To see what the issue is, let's look at this from along the line of sight. Although all of these are identical light profiles, when you rotate them, you'll see that galaxies that are pointed at the observer have a more concentrated light profile on the sky. DESI chooses its targets via aperture magnitude, so we're more likely to choose one that's pointed at us than ones which aren't. So, as a demonstration, I'll remove some of the galaxies which have these less than optimal orientations, go back to the view we had before, and what you'll see is that we're less likely to choose galaxies in these troughs and more likely to choose ones in the peaks. So the density mode in this direction is amplified. The other thing happens in the other direction, except instead, the density mode is going to be dampened. So if you can see, we end up seeing an enhancement of clustering in the plane of the sky and a dampening along the line of sight, which gives rise to anisotropic clustering. When you actually look at this in the survey data, it mimics the quadrupole signature. It's impossible to remove just from observation. And so to deal with it, I have measured intrinsic alignment, simulated the orientation-dependent selection, and modeled how these propagate through to the anisotropic clustering signal. If you want to know more about what actually goes into this, you can come talk to me. I'm going to be here for a while. But for now, I'll just show you the results. What I've plotted here is 1% of what we expect the quadrupole signature to be in DESI for different redshifts. I've also flipped this about 0 because it makes a cleaner visualization. Now, DESI is forecasting F sigma 8 of 0.3 to 0.7%. So basically, we need sub-percent level measurements of the quadrupole. And you can think of these dotted lines as just a rough boundary. If the total errors on the quadrupole get anywhere near these, DESI won't meet our science requirements. And so now I'll show you what the fake quadrupole signature from intrinsic alignment looks like at each of these redshifts. It's is not great. It's significant. So not only will this affect the quadrupole on all scales, but it will be a much bigger issue for higher redshift bins. This is because redder, fainter galaxies are more affected by the orientation selection. And so if not properly corrected for, this will also manifest as a fake evolution of the growth rate, which is really important if you remember this plot from earlier. So bringing us back to the basic question we care about, how does the structure of the universe evolves? If the true measurement looks something like this, just a cartoon, the bias from intrinsic alignment will dampen it, and more so at high redshifts. Of course, this is a dramatic cartoon. The real effect is very small. But the important thing is that it's still a large fraction of our overall error budget. So this effect is a tangle of galaxy alignments and orientation and selection. But I think overall, it's just an interesting reminder that even when you're measuring effects from the largest forces in the universe, you have to think about things that come about because of baryonic physics. These intrinsic alignments can result in anisotropic clustering in redshift space, which mimics the signal used to measure structure growth. So perhaps the next time you see the famous plot of the stick man, you'll remember that it's evolving and think to yourself, an orientation-dependent selection could combine with an intrinsic alignment of galaxies to bias our measurements of the quadrupole of the correlation function. Thank you. And I have, just while we do questions, I have a visualization I worked on of a flight through DESI's year 1 galaxies. It's pretty, so I'll leave it up.
So that was beautiful, Claire. Question. There is also the effect of weak lensing.
Yes?
Right? From the same tidal field, and of course that, as you go to higher redshifts, that could become even more significant. So when you compare your effect, which also relates to the tidal field, to the weak lensing effect from the same tidal field, what is the relative magnitude? Because if you amplify some galaxies by weak lensing, that's a separate, that's from the kappa, from the convergence of the lensing.
Right. So the intrinsic alignment I'm measuring is sort of opposite in sign to the one that you see from weak lensing. And in comparing their amplitude, it really, really depends upon how far along the line of sight you're integrating. It's very important for photometric surveys, but with spectra, we can sufficiently isolate pairs of galaxies along the line of sight so that we actually don't really need to care about weak lensing for the eye I measure for this effect.
But from a theorist point of view, how the amplitudes of the two effects, which one is more important?
Yeah, it depends on the scales, but if you're integrating about roughly 80 megaparsecs along the line of sight, there's comparable in
They are
amplitude.
comparable. And then
Yeah.
as you go to high redshift, the larger distances, is weak lensing becoming dominant? Or?
I'm not quite sure. I would have to.
Nice to know which effect is more important.
Yeah, I think there may be a crossover at some point, but yeah, generally it's not something we care about for this.
Well, we will know the real weak lensing from the lensing of the CMB. This will, I mean, this is an early days thing, but in CMBS4, the entire sky will have its weak lensing map done, and it will be highly accurate.
Yeah, but that's integrated all the way to redshift 1000.
Right.
Whereas if you're at lower redshifts, you're just sensitive to the lenses in front of you.
Right.
So that it's a partial weak lens.
But at least we'll know what it really
The
is all
maximum,
the way up
yes,
to
yes.
redshift of 1000.
Right. More questions to Claire? Yeah.
So have you fed this back into the DESI pipeline in correcting their selection function to mitigate some of this, or?
So the issue is that DESI prioritizes survey speed, and the quality of spectra you get is highly dependent upon surface brightness. So even if we switch our target selection, there's going to be some sort of surface brightness dependence on our final sample, and it's better to impose this implicitly at the beginning, or explicitly at the beginning, and then interpret it later.
There are no more questions. Let's think. Yeah.
live? Okay, it is. Just put it here. All right. Can you hear me? Yeah, I think it's okay. Hello, everybody. So this will be a talk about a subparsec separated unequal mass intermediate mass black hole binary, and this will have a few slides in common with the talk I gave with the discussion we had last week, but not too many. Okay, this is all right. So that's a collaboration with people from a few institutions, and one of them is here. It's Ernesto, who has just arrived as a pre-doc to work on intermediate mass black holes. He's from Chile, well, originally from Ecuador, but from Católica. So he's working on variability. Anyway, so what are intermediate mass black holes and why do we care about them? So these are black holes with the masses between 100 and 100,000 solar masses, and they help us to answer the question, what are the black hole seeds and how did supermassive black hole grow? That's how does it happen? It's because there are two main channels of black hole seeding. It's low mass seeds like stellar mass black holes from remnants of population 3 stars up to roughly 100 solar masses, which grow, merge, grow, and so on. And another hypothesis is the direct collapse black hole seeds that can have masses up to 10 to the 6. So basically you start from something massive, you end up with a redshift 1 billion solar mass black hole in a quasar in a much easier way. However, there's no answer to this question up until now. Everybody started to look for, well, many groups started to look more or less at the same time in the middle of 2000s for optical signatures of AGN in relatively nearby galaxies, so that these AGN are powered by intermediate mass black holes. We joined this race 10 years later, like in the middle of 2010. And we also started from SDSS, but we came with slightly improved methodology on how we dealt with spectra. And here you see a spectrum of a star. A spectrum of an active nucleus on top of stellar population. You have emission lines coming from the galaxy, coming from the nucleus. I'll show it on the next slide. We found 300 candidates, and 10 of them were immediately confirmed in X-ray, and those are galaxies with black holes less than 2 times 10 to the 5 solar masses. So how do we measure black hole mass? So this is a diagram for the AGN. So you have a active black hole in the center of a galaxy with an accretion disk. Then you have a virialized, very dense region called broadline region. It's called broadline region because the lines are broadened by velocities of clouds orbiting the black hole. And here the density is so high that you cannot have forbidden lines like oxygen or nitrogen. You basically, in the optical spectrum, will see only Balmer lines and sometimes helium. Then at the 100 to kpc levels, you have narrow line region, which has lower density and where the forbidden lines are formed from the excitation by the hot corona of the black hole. And this is all sitting in the middle of the galaxy. So basically, you have, if you look at H alpha, you have narrow line that corresponds to this, and narrow lines for nitrogen, but there will be a broad component coming from this virialized region here that is not there in narrow lines. And by measuring its width and flux, we can actually tell the mass of the black hole. Of course, there's a lot of buts, because we can measure it, but the geometry of the broadline region is not really known. The filling factor is not really known. There is dust. There are lots of factors. However, this is the way we can apply to many galaxies, like hundreds of thousands, and look for a needle in a haystack. So, of course, if there are 2 black holes and both are active, you will see 2 broad lines. And that's what this talk will be about. So let me just show this diagram, I won't go into many details. These are scaling relations between black holes and their host galaxies, black hole mass and velocity dispersion of the bulge, and black hole mass and the mass of the bulge. And these correlations have been known since early 2000s, and they were interpreted as the evidence for a coevolution of black holes with their host galaxies, because the bulges grow by mergers and black hole grows by coalescences. So then you would get these correlations naturally. However, if you grow a black hole by accretion, it will go off in this direction. And on the other hand, you might grow a pseudobulge in a galaxy without growing a black hole. Then you'll have outliers in this direction. At this moment, the question is, what are the time scales and what is the dominant mechanism in the bottom of this plot around 10 to the 5 and around velocity dispersions less than 40? So we ran a big follow-up campaign with almost every instrument you can imagine, ground-based, space-based, large telescopes, X-ray satellites, HST, now also JWST, to fill up these scaling relations. And we succeeded. So this is the literature compilation from the from the paper before our study, and this is part of a part of our data set displayed here. Now the question is, can we actually find the evidences for both growth by accretion and mergers in the data? And here are the results. First, we found the Eddington limited IMBH growth. I won't talk much about them because that's subject for another talk, especially given that I have 10 minutes. But we did find a whole bunch of systems, and all the host galaxies of them, interestingly, are late-type disks, similar to Messier 33. So these are not really dwarfs, but they are kind of dwarfish spirals. And they have extremely bright X-ray sources in the centers. And on the other hand, the signal in the optical is so good, and you see that there's no extinction by the Balmer decrement. So if you infer the virial black hole masses, they are all around 10 to the 5. And the Eddington rates, if you convert X-ray into bolometric luminosities, they're in the range between 40 and 200%. So this is one thing. But the most interesting thing, and that's the subject of this talk, is a 13 to 1 mass ratio active binary IMBH. How did we find it? We actually looked at the spectra that we were taking and that we were proposing for follow-up observations. We looked at Sloan spectra and we noticed one object with a hump on the left side. These humps are actually seen in massive AGN, and they are typically associated with outflows. But this was really low mass system, like 1 million solar masses virial estimate. So we decided to reobserve it with MAGE at Magellan in 2021. This SDSS spectrum was in 2004. And we actually found the same line shape 17 years later, and it was the same in H alpha and H beta. And on the other hand, the outflows, the signatures we saw in 03 forbidden line was nothing close to this. We say, okay, maybe that's indeed an intermediate, or maybe this is indeed a binary black hole. We ran our spectrum synthesis code, well, spectrum fitting code to make the decomposition, and we got the two components that would correspond to roughly 10 to the 5 and 1.5 10 to the 6 solar masses. Then we observed it again with Magellan. Then we observed it again with the Russian telescope. Then again with Keck. And the profile has been stable. I mean, the components fluctuate in intensity, but the velocity separation stayed the same for 19 years so far. The source is very well detected in X-ray, and it has optical variability too. But the most interesting news came from the IR, because the IR line shape, Paschen alpha and Paschen beta, is the same as Balmer lines. So we're not dealing with extinction here. And on the other hand, in mid-infrared, we have very strong excess suggestive of a large quantity of warm dust somewhere close to the black hole, but not obscuring our view of the active nucleus. We did some HST work on it as well. And the archival data, this was programmed by Louis Ho, who targeted these galaxies. So this object was known since 2006, but nobody looked at it carefully. And it indeed has a host that is a dwarf elliptical galaxy in the field, which is also a very unusual situation. And it has a disturbed shape. So you can fit it perfectly with two sourcing profiles offset with respect to each other by 300 parsec, which is like 1/3 of the effective radius. We took UV spectra using COS, and we found an asymmetric line profile in helium and in C3, even though the signal to noise is low. But we also found some evidence of something like self-absorption in Lamman alpha and C4, and this is still the stuff that we're trying to understand. So that's my final slide, and here I'm trying to convince you that we're looking at a subparsec separated binary black hole, because if we do the math, we'll get to around 1,000 year period as an orbital separation of 0.2 parsecs. It's of course subject to sin I and to the orbital phase, but the period cannot be less than 100 years, because otherwise we would have seen the velocity changes in 19 years, which we don't. And this gives the a lot of constraints on the orbital shape. So H-alpha lines have almost equal luminosities. So basically, if you take the artist's representation, which I blatantly stole from one of the press releases in the late 2000s, you would see almost equally bright accretion disk, but one will be hotter than the other one, because this one is surrounding the smaller black hole, and it has much higher Eddington rate, like 40%. So I'm listing the alternative explanations, like two galaxies in projection, dust extinction, that is a lopsided broadline region, that black holes are just flying by each other, and none of them seem to work. So we indeed are likely looking at a binary active IMBH, and the main conclusion is that even low mass galaxies can grow by minor mergers, and the occupation fraction at 10 to the 8, which would be an intruder of the main galaxy, is not 0. Well, but we all know it, otherwise we wouldn't have studied this stuff. And that both black hole growth channels are in play in the IMBH regime, so we need both LISA and Athena and Lynx. So thank you.
So Igor, a black hole of 1.5 10 to the 6 is not very far from the Milky Way. It might not correct the...
Yeah, like generally people would call the intermediate mass black holes stuff that is below 10 to the 5. But while you're around 10 to the 6, it's still in the low mass end of these diagrams. If you look here, this is like somewhere around there. So it's somewhere around M32, and M32 is hosted by, is like a kind of low mass galaxies too. But it's really in the area which is not very well studied. And in the this is still like the host is a dwarf. That's what is important. And it's a dwarf in the field, so it wasn't tidally stripped because there's nothing there. Like,
yeah, and because the mass ratio is so large, you can't see the center of light being.
Yeah, you can actually see by eye. If you look at the HST image, you'll see that the center, the nucleus, is offset from the envelope that you can pick up by eye. So that's quite amazing.
Ramesh?
So you mentioned this 13 to 1 mass ratio. Where is the 13 coming from?
Yeah, I mean, this is if you infer black hole masses from the broadline profile decomposition here, then you'll get the bigger one comes from the red shifted broadline. The smaller one comes from the blue shifted one. And interestingly, the radial velocity differences scale is square root of 13. So like roughly it's 2.5. Oh, it's 3.5, sorry. So it's like 300 kilometers per second versus 75 for the red. So that's an additional argument.
Do you have any constraints on the eccentricity, or do you just assume it's circular?
We don't have any constraints on the eccentricity. We can. The only constraint we have is that it's unlikely an unbound. Oh yes, this is my typical slide that I showed at the end of every presentation. So, but anyway, but this is what we have is the like if it is a flyby, you would expect it to have happened from a recent merger from the galaxies, and then you will see tidal tails. But the galaxy doesn't have the tidal tail. So the fact that it is disturbed tells you that it probably happened less than a billion years ago. But the fact that there are no tidal tails tells you that it happened less than 400 or 500 million years ago. So that they already had time to dissipate. So we cannot really tell the eccentricity. We can just claim that most likely this is not a flyby. Yeah, I understand. Yeah.
Accretion can actually induce eccentricity in flybys. So that would be a really cool thing.
Yeah. So we have like the thing that I didn't have time to talk about is that we see coronal lines in the source, and the coronal lines they likely originate from the common envelope of the two, and they are a little bit offset in velocity towards the direction of a small black hole. So it's like if there is a common envelope and it hits it a little bit stronger on one side, so we see it like this way, but there's still a lot of things to dig in the data. It's still work in progress.
We need to go out to take a photo, but
yeah,
just an advice, whenever you show the last slide, stay away from the window.
I'll show you.
Let's thank Igor.